So before I explain exactly what this talk will be about, I just want to, so here's the setting. Huh? So it would be good to sort of commit to memory the main symbols that appear here. But basically this will be, sorry? So this is a talk about function field arithmetics. Huh? So I'm interested in rational points on abelian varieties defined over a global field of positive characteristic. And so here's the setting I will use. So I have, here's my global field, the function field of a smooth and proper curve C over a perfect field. So I mean, in the case of a global field, K, small k would be a finite field, say, you can suppose that if you want. And I take an abelian variety over that big K. And here I take the, and I suppose that A has a semi-abelian model over the whole curve. Or in other words, that it has semi-stable reduction everywhere on the curve. That is something you can achieve after, a finite ramified base change by a classical theorem of Grothendieck. And then here, this is a fundamental object that will be sort of the hero of the whole story. It's this sheaf omega. So that is the sheaf of differentials of the semi-abelian scheme over C, pulled back via the zero section. So that is the, yes, sir?
Point with a pointer or maybe with a cursor so that you know what to point to.
Oh, all right. Here we are. So this, it doesn't.
Maybe
Here we are. No, there it
it's
was.
better if you use the pointer on the computer because that way it's it will show.
I don't understand. What do you mean?
You know what to use the cursor.
Yeah, but that. You mean if I use the mouse? Oh, right. Yes. Okay. Okay. So this is the. So this is it. Huh? So yeah. So this is. So I take the sheaf of differentials of the semi-abelian scheme and I pull it back via the zero section. Huh? So this is also very often called the Hodge bundle. And so this is a vector bundle on the curve itself C, which is really proper. Huh? So here I'm not working over K anymore, but really over the whole curve. And so finally you have the relative Frobenius morphism over K, and this also exists for the semi-abelian model, so I write it in this way. And there's also relative Verschiebung, the Verschiebung morphism, which goes the other way. So if you remember, okay, this is sort of classical in this setting, but what you have is, say you have A goes over C. Here you have AP, so AP is equal to, if you want kind of shorthand for this would be to write it this way. It means it's the pullback, it's the base change of A by the absolute Frobenius morphism on C. And then the relative Frobenius morphism goes like this. And the other way, the Verschiebung goes the other way. So it's and the point is that if you compose Verschiebung with Frobenius, you get multiplication by P. So these are fundamental sort of morphisms associated with commutative schemes, commutative group schemes. Okay, and finally, in fact, I'm going to be interested in points of A in values in this field, I'm looking at the perfection of K, which is the union of all purely inseparable extensions of K. So it means adding simply all the p power roots of points in K. Remember that K is highly non-perfect. In fact, it is the very canonical example of a non-perfect field. So this perfection will include a lot of inseparable points. Now, so here's what I'm interested in. I'm interested in the points of A with values in the perfection. So let me just explain why this is interesting. So if you remember, if A of K, that is say the mod élevé group. So if I make the hypothesis that, say, A has trace 0, means that it has no quotients defined over the constant fields that are simply isoconstant, then there's a classical theorem of Langue, which says that A of K is then finitely generated. And so the question is, now if you take purely inseparable extensions, K of 1 on P, K of 1 on P squared, etc., how is this group going to behave? It is going to keep being finitely generated, but you might wonder whether it will increase. And so the question is really, will it at some point stop increasing? So this is the basic issue here. And so in particular, the question is, well, so under such hypotheses of zero trace, is it true, for instance, that A of Kperf is finitely generated? It's this kind of question that I'm interested in. And this, of course, has applications to sort of model-like questions, because then you can, for instance, look at a curve in its Jacobian, and if you can answer the question for the Jacobian, you have information on the rational points on a curve when you go up this ladder of purely inseparable extensions. Or in other words, if you want, what happens if you take a curve and you take its Frobenius twists, and then you look at rational points again? Are you going to keep obtaining new ones? That's the issue. Okay, so let me just look at the sort of several groups here that we can be interested in. Of course, A Kperf and its structure is the main object of interest. But on the other hand, I suppose it's still best to use this. You can look at this group here. In fact, this group here, I'm not going to say much about this group in general, but one might make conjectures about this group. That is the group of indefinitely p-divisible points in A Kperf. If you have a point in A Kperf, is it possible, for instance, for given rational points to be so that it has an indefinite number of p-th roots which are all purely inseparable? In fact, it's in general, I don't know what to say about the structure of this group. Of course, a prime to p torsion point will have that property, but aside from that, I'm not so sure. Another group you might look at is this one. Okay, this is written in a slightly complicated fashion, but let me just explain what this group is about. So if you look at these twists here, so you have, say, A, so you have A over A, and then you have A of P with the Verschiebung map here, and then you have, of course, another Verschiebung map for A of P. So you have, okay, I will simply always write them V. So you have A of P squared, etc. And then, of course, you might ask, if I take a point P here in A of K, does it have a root, say P1, in A of Pk, which is such that V of P1 is equal to P? And so you might ask the following thing. Suppose I have a point here, and suppose that it is indefinitely Verschiebung divisible, meaning that there is such a rational point here above the point, and then this rational point has another one above it, etc. So what is the structure of that group? So in fact, in general, this question is still open, again. I mean, it's sort of...
IVD is infinitely verschiebung divisible.
Exactly. IVD is definitely verschiebung divisible. So what I've done here is that I have put together, if you want, the indefinitely verschiebung divisible points of k, and then those of k1 on p, and then those of k1 on p squared, etc. I've bundled them all together. But basically what it is simply is you take either k or one of its finite purely inseparable extensions, and then you look at the points which are indefinitely verschiebung divisible in this sense. Okay? So this group is related to the first group, because it's a subgroup. Because in fact, you see, if a point is indefinitely verschiebung divisible, well, then if you take if you take a pth root of the point, it must be purely inseparable. The reason being simply that Verschiebung times Frobenius equal multiplication by p. So if you go up like this, I mean, nothing happens. And then here you have a purely inseparable extension coming from the Frobenius. So clearly, a point with this property will be indefinitely p-divisible in the group of perfect points. Okay. But in general, of course, it will not coincide with it. It's a subgroup, it's a proper subgroup in general of that group. On the other hand, when A is ordinary, then these two groups coincide. So remember, ordinary means that the Verschiebung is étal, is an étal map. So in that case, clearly, you will have, it means that inside the Verschiebung there's absolutely no purely inseparable part. So clearly in that case, the two groups coincide. On the other hand, if A is, also remember that if A has P rank 0, which is the same thing as saying that V, the Verschiebung V itself is purely inseparable, so that both the Verschiebung and the Frobenius are purely inseparable, then in fact any point is indefinitely p-divisible, because the multiplication by p is purely inseparable. Okay. So. Now, I want to present a few conjectures that have been made over the years about these groups. So the situation is still very poorly understood, in spite of the fact that it's sort of quite irritating. But now, so let me so I'm going to state a few conjectures. And from now on, suppose for simplicity, so I suppose always that the trace of A is 0. So that means A has no quotient varieties which are isotrivial. That means defined over small k, over the small field. It's sort of highly non-isotrivial, if you want. And in this situation, as I mentioned at the beginning, remember A of k is finitely generated. Okay, so this is the sort of geometric version of the Mort-Delvey theorem called the Langue-Néron theorem. And so now the question is A Kperf finitely generated? So obviously not. So that's certainly not true, because if you take an abelian variety with p rank 0, as we just saw, a point is indefinitely p-divisible, and then that cannot happen in a finitely generated group. So that's not true. But nevertheless, you might conjecture the following. I mean, the first one, I would rather see that as a kind of question than a conjecture, because I'm very unsure about this. But you might wonder whether A Kperf is finitely generative if A is ordinary. So this is something that was, I think, for the first time discussed by Thomas Scanlon. It was also discussed by Paul Ziegler later on, and also in work by Gierke and Musa on these, on sort of model, so function field model kind of questions. And on the other hand, Eno and Lange have explicitly asked whether IVD of A Kperf is finite and of prime to p order. So there is that question. I mean, is this finite in prime to p and of prime to p order? And in fact, in their case, their motivation comes from a different angle. It comes from sort of this has something to do with Hélène Hénault's proof of a conjecture of Giesecker about stratified bundles. And it's a kind of natural abelian analog of something that happens over projective space. Because if you think about this, you can express this point in IVD. This can be, you can express this in terms of line bundles, because, of course, this is the dual of its dual. So you can view every point as a line bundle, and then if you want, this becomes the condition a line bundle, and having another line bundle on here, so that the pullback by the Frobenius is this line bundle, etc., etc. I mean, you can simply translate this into a question about line bundles, and then it becomes interesting in the context of Hénault's original question. And also, in fact, Hélène Hénault asked this. So this was in a sort of in a whole email correspondence I also had with Hénault and Langue some 10 years ago, whether this here is a finite order. So, or in other words, is it possible, so if you look at the torsion group in a Kperf, so it falls into, of course, prime to p part and p part. So there's the pre-primary part and the non-p primary. So if you look at non-p primary, that must be finite. Because simply if you take a torsion point and you divide it by n with n prime to p, that's étale. So this will not live in a Kperf. It will simply be finite because a of k is already finitely generated. On the other hand, on the purely p part, the pre-primary part, this is not clear. You see, you might wonder, is it possible to have a torsion point, a p torsion point, which is indefinitely p-divisible in the group? So the conjecture is here, this is not so. Okay, so in fact, on all these conjectures, one can make progress, but not in full generality. So, and finally, I just want to mention this here, which is sort of a related question. It's both related and unrelated, because in a way it's related only, in a sort of indirect fashion. But you can also ask the following. So this is a generalization of the model Langue conjecture, if you want, which says, so if you have in X's in A is a subvariety of general type, then you might wonder whether so you might conjecture that X Kperf is not Zariski dense in X. Sorry, I forgot the is. So remember that by the model Langue conjecture over function fields, X of k is not Zariski dense in X. And this is something that has been proven. This was proven for the first time by Rössler in '96. And then other sort of proofs were given some 10 years later. And, but the question is, again, I mean, is it true that X Kperf, so if you simply keep twisting, if you want, basically it means if you twist the curve, you might get more rational points, but can you get so many more that in fact you're going to fill up all of X? And so one might conjecture that not. And so of course this conjecture is related to, for instance, the conjecture on finite generation on finite generation when A is ordinary, because if a Kperf is finitely generated, well then it is true that X Kperf is finitely generated. I mean, that is the content of Rössler's proof work. Okay, so now here's what is known about these conjectures for the time being, and I'm going to discuss some proofs of these statements. So, so you can prove the following thing. So you can prove that indeed a Kperf is finitely generated if if the base field K is FP bar, and if A is ordinary, so this is as conjectured, but it has to be then geometrically simple, and also, so calligraphic A should not be an abelian scheme. That means there should be a point of bad reduction. So if you want, in other words, if A is geometrically simple, is ordinary, and has a point of bad reduction, then this is true. Okay. So in fact, you're left with the quite sort of irritatingly sort of slick case of a variety with everywhere good reduction. And this, of course, is sort of familiar. For instance, for those familiar with these kinds of questions, there's this question of the Bogomolov conjecture over function fields, where precisely that situation, everywhere good reduction, was open for a long time. In fact, I think it was only solved recently. So in this situation, I don't know an answer in the situation where there is no bad reduction at all.
How serious is the requirement that geometrically simple? I mean, can't you break it up after an extension?
Yes, of course. You can use Poincaré reducibility and then state it for each yeah. And also this question, this is of course invariant under isogeny, so you can look each simple factor separately. Yeah. But it's just that you might have, for instance, a product of something that has everywhere good reduction with something that doesn't, and then, yeah. Yeah, and so this, so I'm going to explain a few things about the proof of this. So in this generality, this is due to me, but when you look at an elliptic curve, this was proven by Gioca some more than 10 years ago already. So remember, in the case of an elliptic curve, of course, there is no elliptic scheme with everywhere good reduction. So basically, that settles the problem when you look at an elliptic curve. And so you can also prove the following thing. So you can show that, so the conjecture of Henault and Lange is true. So it's that it is torsion and finite of prime to p order if small k is fp bar. But in that situation only. I mean, if you replace k by, say, a large algebraically closed field over a positive characteristic, I don't know how to answer that question.
So this looks like a strong condition, and A is an abelian scheme.
What did I... Oh, just one. This is bizarre. Why did I formulate it in this way? So... No, but actually this is odd. I must have switched around some things with the previous sentence. In fact, you can... No, sorry. This is due to this. So this is formulated, I hope this is not misleading. So what Henault and Lange proved in their original article where they formulated the conjectures, they proved it when the situation where A is an abelian scheme, so good reduction everywhere. So in fact, you see, it's exactly the opposite situation. There they could prove something, and that's in the situation which is problematic in the previous sentence. But on the other hand, I then later on, I mean, more recently, I gave a proof in general when if k is equal fp bar. On the other hand, their argument works irrespective of whether k is equal fp bar or not. So that is the difference. Yeah, and also, so very recently, Marco D'Adezio and Emiliano Ambrosi showed, in fact, again, this conjecture of Hélène Henault in the situation where k equal fp bar. So indeed, tau a Kperf is finite. So, and also one has to see the techniques used here are very variable. So for instance, the technique used by Henault and Lange uses simply a computation of heights. D'Adezio and Ambrosi use heavily used isocrystals. So it's a very sort of, it's a very p-adic proof in a way. And I use yet another technique which I'm going to talk about. Yeah, and finally, as far as the sort of Mordell type statement is concerned, so this is indeed true if X is a curve and K is a finite field. So this was proven by Min Young Kim in an article in '98 or something already. And as it happens, the technique introduced by Kim to prove this is very much what led me to these more general techniques I'm going to talk about now. So for me, this is really the beginning of the story. Okay, so remember the situation we're in. So we want to study a Kperf. So how do we go about this? So to do this, there's a very classical tool that is the classical theorem which is available, but which in fact strangely was, I think I was the only one to think of using this. Although it's, as you can see here, it is very natural in this context. So here's the statement. So this is a theorem by Artin and Milne. This appears in an article, I think, at the end of the 60s, and is then also reproduced in Milne's book, Arithmetic Duality Theorems. And this is called the second canonical isomorphism, or something, second canonical exact sequence. And so in this situation, this is a more general theorem, but in this situation it says the following. So if you look at the torsors under the kernel of Frobenius, so H1 FPPFK FAK, so this is the standard notation for that. So if you look here so here you look again at Frobenius, then you have the kernel of Frobenius, and you look at the torsors under that infinitesimal subgroup scheme. That's H1 FPPFK FAK. Well, there's a canonical way to embed this into the homomorphisms between two K vector spaces. And so these K vector spaces are, well, so omega K, so that means it's the stalk at the generic point of omega. So, or if you want it simply, if you remember A over spec K, so it is simply the stalk at 0 of the sheaf of differentials of A over K. And then you have to you twist it by Frobenius if you want. So it's and so this is a K vector space, finite dimension, the dimension of the abelian variety, and it embeds into the homomorphisms between this vector space and again the stalk at the generic point of the sheaf of the differentials of big K over K. So these are very different objects. So you have spec K, but then spec K, of course, itself also has sheaf of differentials. This is affine, so it's simply the sheaf of differentials of this. This is a K vector space of dimension 1. Okay. Now, in our context, this is not very useful because obviously, if you look at K rational points, you're going to end in this group, which is, of course, infinite. So you really need a little more information in a geometric situation. So that is, you need to, for instance, if you take and so this is a very classical story, of course. If you take a rational point in here, so if you take a rational point here, then a rational point will give rise to a torsor, because simply you take the inverse image of the rational point, and the kernel of Frobenius acts on the inverse image. That gives you a torsor. And so that gives, in fact, again, I mean, very classically, it gives an immersion of, an embedding, I mean, between this here and H1 FPPF of KFK. And so the image of this So this naturally embeds in this, and then this, of course, by this theorem, naturally embeds in that. But now, so we are really interested in the image of this. Means we're interested in the points in AP of k, the k rational points in here, which in fact, well, we're ultimately interested in those that are 0 in here. That means that are in the image of Frobenius. But we're interested in a subgroup, which is the image of this one. And yeah, and now the question is, if you take a rational point, you take the corresponding torser, can you say anything about the poles and zeros of this homomorphism? Because if you look at this homomorphism, so this is all defined over big K. So if you want in geometric terms, big K is the generic point of C. So we are looking at rational functions. So K is the set of rational functions on C. So if you look at such a map, you might simply wonder, if you choose, say, bases, so what are the poles and zeros of that map over C? And so this is what this theorem does here. So in fact, here I've written something already for slightly a point which is for a group which is more general than the image of this one. So this is called the Zelmer group. We are in fact not really going to need the Zelmer group in this situation, but the Zelmer group is a group which contains the image of this. So you have the image of this in here, and the Zelmer group is slightly larger. It's defined only by local conditions as opposed to being a completely global group like this. But if you look at that group, and so in particular at the image of the rational points, in fact, you see the poles and zeros are very mild. That means you will, in fact, on the level of f pull back k omega k, you can simply take the whole of omega, and on the target, you have to twist by e. That means that you have at most a pole of order 1 along e. Now, what is e? So that is actually defined at the top. So that is simply the points where the abelian scheme has bad reduction. So the points where there's really semi-abelian reduction. So there's only finitely many, and it's along there that you might have poles. As it happens, if you look at Artin-Milne's theorem, it will suppose you have none at all. Suppose that the whole scheme is abelian. Well, then this theorem is almost automatic. This is a consequence of Artin-Milne, in fact. So the whole problem is when it does not have a good reduction everywhere. Okay. So yeah, so this theorem, so this is the basic tool. It's this theorem, and yeah, in fact, I should have remembered better what came on the next slide. So this is what I actually wrote. So you have this group is contained in the Zelmer group, which is contained in there. And so this theorem can be proven in two different ways. So one way to do this, which is the one I used originally, is in fact, you use semi-stable compactifications of the semi-abelian scheme. And then you you work on the semi-stable compactification. You sort of treat it as if it were smooth, and you use logarithmic, a sheaf of differentials with logarithmic singularities instead. But the point being that the Artin-Milne map can then be very explicitly described in very geometric fashion when you look at a rational point. So the Artin-Milne map is in general sort of defined in abstract fashion. But if you look at the torso associated with a rational point, there's a very geometric way to do this, which will naturally involve the logarithmic geometry of the compactification. And the thing is, it's a little bit tricky because you have to use Folting's-Chai compactifications, the universal compactification of the semi-abelian scheme on the moduli space. You cannot actually use compactification on C itself. The problem is that this will lead to field extensions which you don't want. So you have to sort of bootstrap yourself somehow to, well, this situation. But you can also prove this directly by actually using these, so-called Renault uniformizations at the points of E, the points of bad reduction. So for those who know what that is, And then it is really a direct computation in FPPF cohomology. So this is something that's being done by my PhD student, Vous, right now. So. Sorry, how's the?
How is the Artin map defined?
Well, yeah. I can tell you how it's defined for a rational point, if you want. So that's, oh, actually, no. Okay, no, I can give you the general definition. So let me just. Yeah. So the Artin-Milne map. So you take, say, you take T over spec K. So that is so this is a kernel of FAK torso. And then you look at the, here you look at absolute Frobenius over spec K. And then you simply look at the associated Cartesian diagram, so it's TP if you want. Okay. And the point is that TP, so this is something you have to prove, but TP is a trivial torso. That means if you pull back for Frobenius, you will actually kill the torso. So it means that there's a section, and this section is actually unique because this is in a purely infinitesimal group scheme. So this is, say, epsilon. And yeah, and so therefore, so let me just see. So therefore you have epsilon, yes. And so you can compose both. So this is the composition of both maps. So let's call this phi. And in particular, you have a sheaf of map of differentials, T, omega T over K goes to omega F K. Yeah, and on the other hand, this here is naturally isomorphic to omega, yeah, omega okay, so sorry, I hope this is still legible here. Okay, so what do? I take the torso, I pull it back, then it has a section. So I take this section and I look at the composed map, so I get this map phi, this morphism phi. And so since this is a morphism of spec K schemes, since this commutes, yeah, you therefore get a natural map of differentials. So you get a map of differentials from the pullback by phi of omega T over K to the sheaf of differentials of Fk. Now, on the other hand, this here is, of course, the same, since this is the composition of two maps, it's in particular the same as the sheaf of differentials of this here, restricted by epsilon. But now Tp is trivial. So in fact, this is the same thing as that. So you get, so entirely in terms of the torso, that gives the pullback by K of omega of the sheaf of differentials of the kernel of Frobenius, so over K, to the sheaf of differentials of the Frobenius itself. But on the other hand, in our situation, this here is precisely the pullback of omega. And this here, in fact, the sheaf of differentials of omega is precisely omega K over small k. This is a classical computation on the done in Hartshorn, for instance. So this is equal to omega k k. So that's the map. Okay, so it's yeah. Now, if you now going back to this theorem here, So you have this embedding, but now the interesting thing about this is that you see, now this is a global statement. This is not a statement about rational functions. So here you have homomorphisms between two vector bundles. So for instance, suppose that you were in the situation where small k, the ground field, small k is a finite field. Well then, for instance, the right-hand side here, the target of this arrow is a finite group, because it's a set of homomorphisms between two global vector bundles on a projective curve. So this is a finite dimensional small k vector space, so FP vector space, so it's finite. So in particular, it shows that the Zelmer group is finite. So this is another way to show it in this situation. But the interesting thing is that now if we're interested in, remember that we're interested in twists. So we're looking at A of k, but we're also interested in a p of k, p squared of k, etc. So we're going to look at twists of A, in which case I'm going to replace here omega, in fact, by further powers pullbacks by the Frobenius. So I'm going to pull back by Frobenius, but then I'm going to do it again. I'm going to look at omega pulled back by a power of Frobenius. And the interesting thing is that here now comes the theory of vector bundles can be used. Because, for instance, look at a very simple example. Suppose that omega is a line bundle of positive degree. If omega is a line bundle of positive degree, well, if I pull back omega by sufficiently large powers of Fc, well, I will make the degree increase as much as I want. Now, if the degree is very large, then clearly there cannot be such a homomorphism, because this is fixed. Omega CKE is a fixed line bundle. And then if I make the degree of this extremely large, there will be no more homomorphisms. So in that case, you will have shown that the Zelmer group is in fact trivial. So basically that is exactly the kind of line of reasoning I want to make. So I want to use global geometric properties of omega and of vector bundles to deduce things about the Zelmer group. Now, yeah. And in particular, so the global theory of vector bundles, that of course involves semi-stability. So this is what I'm going to do, use the theory of semi-stability of vector bundles, and especially in the positive characteristic context, which is more problematic, and also the so-called Harder-Narasimhan filtration to study omega. And now, just to understand the logic of the remainder of the talk, so what I'm going to show is that if you look at the Harder-Narasimhan filtration, it will give you information about this group of homomorphisms. On the other hand, what is interesting is that it will point out certain natural subbundles, or quotient bundles of omega. And as it happens, but this is not expected at the outset, these quotient bundles will in turn be related to the structure of this group scheme kernel of Frobenius. So there will be a kind of, it will sort of point back to the group scheme. That is, if you look at the Harder-Narasimhan filtration, the structure of omega, this will point to certain quotient bundles or subbundles, and these in turn will point back to the group scheme itself. And so once that sort of loop, you've gone through that loop, then you end up with more information about that group scheme, and then you can sort of start the loop again somehow. Okay, so before I explain this, let me just remind you what the Harder-Narasimhan filtration of a vector bundle is, because this is quite important. So if you don't know this terminology, this wouldn't make any sense. So, here's a crash course. Okay, so omega has a filtration. So like any vector bundle on small c has a filtration of this type. So you have a subbundle and then another larger bundle and etc. With both, but in it's strictly increasing, so they never repeat themselves. And the quotients in this filtration are semi-stable. So, and with strictly decreasing slopes. Okay, so of course you have to know what a semi-stable vector bundle is. So I will just say it in words in a moment, but it will, you basically don't really need to know anything about it. So, and here's the definition of the slope. So here you write mu max of omega, so that is the slope, mu stands for slope. That's mu of omega 1, and it's the slope of omega 1, which is the very first bundle that appears in this filtration. And the slope is by definition the degree divided by the rank. Okay. And finally mu min, so that's the slope of the quotient of omega by the very last one. Slope of this, and this is that. And so the point is that in this filtration, the slopes of the quotients are strictly decreasing. They're strictly decreasing, and the quotients are semi-stable vector bundles. And so with all these properties, if you put all these properties together, that is the Harder-Narasimhan filtration. So the theorem of Harder-Narasimhan is that any vector bundle has such a filtration, and it is unique if you require these properties. Okay. So that is the Harder-Narasimhan filtration. Now the fundamental question in characteristic P, which does not arise in characteristic 0, and which has been less studied than in characteristic 0, is what happens to the Harder-Narasimhan filtration when you consider Frobenius pullbacks. So if you take omega and you pull it back by Frobenius, well then, of course, you can pull back the original filtration, and you might wonder, is the pullback of the original filtration also the new Harder-Narasimhan filtration? Now, this is not so. But nevertheless, and that is an interesting, very interesting point, so this was proven, this was proven in any dimension, in fact, by Langue, but I think the case of curves that we need here was proven earlier, and I forget by several people, I think. But you can show that, in fact, so the Harder-Narasimhan filtration is not stable under Frobenius pullback, but it will ultimately become stable. So if you keep pulling back, at some point it will stabilize. So it's and so therefore, it in particular makes sense to define these new invariants, which is mu bar max and mu bar min, which is simply the mu max of some Frobenius pullback divided by Pn, and then you let n go to infinity. So if you look at this, because the statement of by Lange's theorem, if you want, in both these limits, the sequences, in fact, are ultimately constant. They're ultimately constant, so it makes sense to talk about the limit. So this is sort of the Frobenius asymptotic, if you want, or stabilized slope of omega. And now, here's a very basic fact of this theory. And this is, in fact, of course, this is the one thing that matters for us. So it's the fact that, so if mu bar min v is strictly larger than mu bar min max of w, well then there are no homomorphisms between v and w. So if you take any two vector bundles on C, and they have these properties, then that is so. In fact, usually you see this condition formulated for simply mu min and mu max. This is also true, of course, just mu min and mu max. But in particular, it will be true for mu bar min and mu bar max, which is what we are interested in. So in fact, this is the fundamental property of this of the minimal maximal slope that are of interest to us. It's a numerical condition for this group of homomorphisms to be 0. And so in particular, here you see, so this is a generalization of what I said before with the line bundles. So if, for instance, mu bar min of v is strictly positive, well then if you pull back sufficiently many v sufficiently many times, you cannot have any homomorphisms between the pulled back v and w. Because of course, if mu bar min is larger than 0, then if you pull it back by nth power of Frobenius, you will multiply mu bar min by Pn. That's simply from the definition of the mu bar min. and that will then ultimately become bigger than mu bar max. So that is very useful. So this is a okay, so remember, so that this is exactly what the kind of thing we want to do. So for instance, before we even go further, imagine that these simple facts have the following interesting consequence, which is that if, without either going to the next one, simply to convince yourself that this is quite elementary, if you, so here, look at your A over C. So you have your omega. And suppose simply that mu bar min omega is strictly bigger than 0. Well, then it means that, okay, if I replace omega by a sufficiently large power of omega, then there won't be, so it means that hom C f n star of C omega to omega C over k of E is 0 for all n bigger than 0. Now, of course, this here is not the bundle we want. Remember that in the Artin-Milne map, we only had n equal 1. But that doesn't matter. We can replace this by a twist. If I replace this by a twist, I will replace omega by the pullback of omega by a power of Frobenius. So it means that I can simply take APN, and that will indeed have this here as a Hodge bundle. So in fact, what it means, so if this is true, very simple, this is true, well then the Zelmer group of a sufficiently high twist of A, the Zelmer group of the Frobenius, will be 0. So that's simply what it means. And on the other hand, this condition here, this is quite interesting, this here, it can be proven to be exactly equivalent to requiring the Hodge bundle to be an ample vector bundle. So if omega is an ample vector bundle, then definitely we have the Zelmer group will end up being trivial after twists. Okay, so in fact I'm going to repeat part of this on the next slides, but this was just to convince yourself that this was elementary. But now, okay, but here now I'm going to become a little more detailed about this. So first, there's one point which I have not mentioned at all, which is that the line bundle, the vector bundle omega is actually, if you're endowed with some supplementary datum, gives you back the kernel of Frobenius. That means the kernel of Frobenius is entirely described by omega together with another supplementary datum. So this is what I write here. So you see, look at the kernel of Frobenius. So here, look at the kernel of Frobenius on the whole abelian scheme. So it's a finite group scheme over C. Then, as it happens, so the co-Lie algebra of G, so that means the co-Lie algebra is simply the dual of the tangent of the Lie algebra of G. The dual of the Lie algebra of G is simply omega. So it's easily computed. It's exactly identified with omega. And also, if now you have a natural map from omega to pull back by C of omega, which is given by pull back by Verschiebung. So simply pull back by Verschiebung of differentials. And so if you look at omega together with this structure, so this is a so-called P co-Lie algebra, the dual notion to a P Lie algebra. So it's a P co-Lie algebra over C. And now there's a classical theorem that says that the category of finite flat group schemes of height 1 over C and P co-Lie algebras, these are anti-equivalent categories. So it means if you have the P co-Lie algebra, you can recover the group scheme from it. A finite type group scheme of height 1 is one which is killed by Frobenius. So of course the kernel of Frobenius is killed by Frobenius. So, so this is quite interesting. So this means that in this situation here, for instance, when we look at now Harder-Narasimhan filtration of omega or something, we very much want to know how this filtration behaves with respect to the Pico-Lie algebra structure. That is very important because then we might get information about the kernel of Frobenius. That would be much better. So here's a proposition now in this direction. So suppose that first suppose that the Harder-Narasimhan filtration of omega is Frobenius stable. So in fact that means that if you pull back by Frobenius, you recover the Harder-Narasimhan filtration of the next step, and also if you keep going. So remember, you will always be in that situation if you pull back by Frobenius sufficiently. Well then, as it happens, the quotient of non-positive maximal slope in the HN filtration are Pico-Lie algebras. And the quotients of strictly negative slope are bi-infinitesimal group schemes. Bi-infinitesimal, it means that it's infinitesimal and the dual, the Cartier dual of the group scheme is also infinitesimal. So it means that there's a partial compatibility between the Harder-Narasimhan filtration and the Pico-Lie algebra structure. But it only corresponds to, if you want the quotients in the Harder-Narasimhan filtration, which are 0 or negative. Anything positive is purely geometric, does not have there's no link. And so the way I came on this here was, it's a very windy way, but in this formulation, this is inspired by a result by Jean-Benoît Bost in characteristic 0, where he in fact does not look at finite group schemes, since this is of no interest in characteristic 0, but he looks at formal groups. So there's a kind of analog of this for formal groups in characteristic 0, which is looks very much like this. So, and now there's the following interesting thing is that, so using this simple proposition, you can prove the following proposition, which seems very harmless, but it's not as harmless as it looks. So this is a global statement about finite group schemes of height 1 over C. So it's very much a statement over C in a projective situation. And so what I'm saying is that there exists in G a largest multiplicative subgroup scheme of height 1. There exists the largest such object. And so if you have any other multiplicative group scheme of height 1 mapping to it, it will map through it. And this is called G mu, and it's compatible with Frobenius twists. And the existence of this group should not be confused. This has nothing to do with, for instance, you cannot deduce this from statements about Galois representations. This is very, although it looks like you could. So it's a purely, especially because it's compatible with Frobenius twists, it's really a completely global statement over C. And to do this, you need this, in fact, although the Harder-Narasimhan filtration does not appear here, you need this theory to prove this. Now, so here are some things you can show. So of course now you want to know on the what is G mu? I mean, what can you say about this G mu? So I assert that there is such a group, which is the maximal multiplicative subgroup scheme of G. So for one thing, so again here, you suppose omega, you've pulled back enough so that the Frobenius stable, the HN filtration is Frobenius stable, and you also suppose that the minimal slope is not strictly negative. So minimal slope, that is actually, it has to be exactly 0, neither strictly negative nor positive. So then, in fact, as it happens, the G mu is given by the quotient of minimal slope. That is by omega divided by omega rho. So what I'm saying is that the Pico-Lie algebra of G mu is omega divided by omega rho. So it's given by the quotient of minimal slope. And if, in fact, the mu min is strictly positive, then G mu is trivial. And also here comes another point, which is, in fact, again, sort of quite analogous to what happens in characteristic 0, which is that if A is ordinary, then in fact, mu bar min is larger equal to 0. So you will have no biinfinitesimal, no quotient strictly smaller than 0. In fact, if you think of what I said about the fact that the quotients of strictly negative slope would be biinfinitesimal, this should be quite clear, because they are not allowed in an ordinary abelian variety. Okay, so, and now, okay, I need a couple more minutes. So now here is, we are now going back to the original problem. So we have the Artin-Milne map. Now we take a point, say, in some Frobenius twist, and we look at the corresponding map we get there by the extended Artin-Milne map. And so now here's what one can show. So this is, in fact, a very easy consequence of the previous statement about the fact that mu bar min is of an ordinary abelian variety is strictly larger than 0. But this here will factor through the co-Lie algebra of G mu. This is an easy calculation, but I mean, just believe it if you don't want to make it just now. But so this map will factor through this co-Lie algebra. And here's another statement. This is harder to prove, but it's basically also a lot of combinatorics with maps between with the Harder-Narasimhan filtration. If you take an indefinitely Verschiebung divisible point of a sufficiently high twist, it will again factor through the co-Lie algebra of this infamous group G mu. So this seems to be a kind of a basic thing that happens in this situation. You have this group G mu, and in critical situations, the Artin-Milne map factors through this group. Okay. So of course, this has dramatic consequences. It means that that is dramatic if you know something about G mu. So if you know that G mu is 0, then of course you know the Artin-Milne map is 0. So that's definitely something you want. Okay, so now if you look back to the original problem, which is, you remember, the structure of IVD and the structure of AK Kperf, so this is very much related because, so if you look at the last two results about the factorization through the P-co-Lie algebra, so AK Kperf will be finitely generated when A is ordinary and if G mu is equal to 0. Because it means that at some point, everything will have, there will be no more Frobenius roots if you take sufficiently high twists. Again, I mean, you have to unwind the definitions, but it will imply this. And also similarly, if G mu is 0, then IVD, in fact, of a sufficiently high twist, so therefore, in fact, also the original IVD would be P divisible. And if, since this would be P divisible and of finitely generated, it would have to be finite of order prime to P, which is what you want. So therefore, on the other hand, the problem of the structure of AK Kperf and the problem of the structure of IVD is something which is invariant under isogeny. So therefore, what you might want to do is, if G mu is not 0, well, then you might replace it by another variety where G mu is 0. So we seek to replace A by an isogenous variety where G mu does vanish. So therefore, okay, I'm over time already, so I'll be very quick here. So therefore, what you do is a very obvious thing. You take A, you quotient it by G mu, and then you take the new G mu, you quotient it again, etc. And the question is simply, what is this sequence like, and can it be infinite? So these are sort of very basic questions. I mean, the basic question is, is it always finite? And more generally, a weaker question, does the sequence, if it's infinite, contain only finitely isomorphism classes? So these are questions. And in fact, in general, this is a kind of basic concern to understand which varieties have an infinite mu sequence, if you want. I don't know how to answer that question in general. But nevertheless, you can show the following things. So if you look at FP bar, then there will be only finitely many isomorphism classes. This is because you can compute the modular height of the quotients, and also you can show that the whole sequence descends to a finite extension of FP. And then you use an argument very much like in the proof of the Tate conjecture over finite fields by Tate to conclude that there's only finitely many isomorphism classes. And also, and this makes it a bit more mysterious, if in fact still you have FP bar and the sequence is infinite, well then actually this forces good reduction everywhere. It does force it absolutely everywhere. And the reason for that is, in fact, you use the previous proposition to exhibit an étale endomorphism of degree of power of p, and that has very, very strong geometric implications. Okay, so the corollary of all this is what I sort of announced partially at the beginning, which is that, so if A is ordinary and A is not an abelian scheme, so of course then the sequence has to be finite, and therefore you can reduce to the situation G mu is trivial, and then you know that a Kperf is finitely generated, so you're in business. And on the other hand, we also know that, in fact, if it has everywhere, if it is an abelian scheme, well then IVD a Kperf is a torsion group by nous and Langue, who actually exploit this case, in this situation. And then, of course, you've already proven the result. So basically, this reduces the question to a nous Langue. And if you combine it with the fact that Adetiso and Ambrosi have already shown that this torsion group is finite, you then get the fact that this is a finite torsion group. So, right, I'm so sorry for doing 6 minutes overtime. So that's it. Thank you very much. Yeah?
So when you were saying the question is like, does that sequence always terminate? Do you know examples where it doesn't terminate, or could it be that it always terminates?
No, it could be that it always does. This is very bizarre. I just don't know much about that actually.